In this video lesson, we're going to learn about covalent bonding, and we'll learn how to determine whether a compound is polar or not. So remember from an earlier lesson that covalent bonding occurs when two atoms with a delta En of 1.7 or less occurs. So the electrons are shared and they're not transferred like in ionic bonding. And it occurs between two nonmetals. And covalent bonding forms molecules like water, carbon dioxide, methane. It also produces giant covalent structures like diamond. We'll learn about those types of structures in a later lesson. So in this image, we can see this is the bonding between hydrogen. So remember, hydrogen has one proton and one electron. Their valence shells have overlapped, so that the two electrons that they each have are being shared between each other and completing their valence shell. So now they're satisfied and they're stable. So what we do to figure out the chemical formula and the type of bonding that happens is we use the octet rule. So electrons need to be arranged so that their valence shells are filled. So we have to overlap electron pairs so that we can satisfy their octet. Remember, except for hydrogen, everything will want to have 8 electrons in their outer ring or their valence. So this can be done by forming a single, double, or triple bonds, and we'll talk about those examples in a second. If there still are extra electron pairs, they can be placed on atoms as well. If you've satisfied the number of bonds that they can make, you can also then put extra electron pairs. So if we look at the first example, this is just 3 ways of showing hydrogen. So like we said before, each hydrogen would have 1 electron in its valence. This is the Lewis structure showing that they're sharing the electrons. You can draw Bohr diagrams if you wish to show, but that's a little bit tedious. This would be what the model would look like if you were building it. And this is called the displayed formula. So after you've figured out that that's going to be a single bond, you'll just draw a line to represent a bond instead of the 2 dots. This is oxygen right here. So oxygen actually has 6 electrons, so 2 of them will share between each other. So that would make 1, 2, 3, 4. And then they'll still have 4 electrons each, so 5, 6, 7, 8. So this one is satisfied. This would be the displayed formula, or you would also possibly draw the extra electron pairs. This is a model of it as well, so this would be the Lewis structure. Nitrogen, same thing. It has 5, so it wants 3 more, so it's going to share its 3 of its electrons with each other to make a triple bond. This one had a double bond, and then they'll still have a pair left over, so that will be 2, 4, 6, 8. So it satisfied the octet. So in these cases, we put extra electrons to demonstrate. So the way you create Lewis structures or Lewis diagrams would be that first of all you need to count. You need to count the total number of valence electrons you will have for all the atoms in the compound. Then you'll draw the central atom with the ligand, which is just the ones on the outside, atoms around it. So if it were CH4, that would mean that the carbon is the central atom, and the hydrogens all around it are the ligand atoms. Then you're going to fill in a bonding pair between each of the ligand atoms and the central atom. And then count that up, see if you've created the octet, and then satisfy the outside atoms to fulfill the octet rule using leftovers electrons. And if you have any leftover, put them on the central atom or use multiple bonds. So that is how you do a Lewis structure. So we'll go through 2 examples. So this one we have 2 electrons total. I'll switch over to my pen. So we have 2 electrons. So we'll draw our 2. There won't be a central atom in this one. Each of them has 1 electron, so this is going to become that. The next one, methane, So we have 4 from carbon plus 1 each from hydrogen. So that's equal to 8 total. So I'm just going to move over my carbon over here so we can have room to draw. So we're going to draw our ligand atoms around. So hydrogen, 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 hydrogen. So the first step was to put a bonding pair between each one. 1, 2, 1, 2, 1, 2, 1, 2. And then that's taking care of all of them. We can see if it satisfies each of their valences. So hydrogen can only have 2, and each of these hydrogens has 2. And then carbon has 2, 4, 6, 8. So we have satisfied the octet. This is the molecule that you would draw. You could also draw it in the displayed form, so like so. Now that we know that they're single bonds. So we'll go through another example. So this one, we have water. So we have 2 hydrogens that each have 1 electron. And then we have oxygen that has 6. So that's a total of 8 that we need to distribute. So we'll draw our oxygen. Just a hint, the one that has the, that there's usually a single one, that's usually going to be your central atom. And then you'll draw your ligand atoms around it. So I'm going to draw it like this. So the first thing we need to do is put a bonding pair between each. So that now satisfies hydrogen, but we still have 4 more electrons to distribute, so we need to put lone pairs on oxygen because you can't put any more on hydrogen. They can't accommodate anymore. Their valence only can hold 2. So this is what it would look like. The actual shape of the molecule we'll learn about a little bit later. If you were to draw the display form, it actually looks like this. So water actually has a bent shape, and that bent shape is because of these lone pairs of electrons. We'll learn about Vesper theory in a later lesson, and that will help you identify what shape a molecule will be. We'll also see that when we build our molecules of different substances later on after this lesson. Our next one is carbon dioxide. So carbon has 4, and then there's 2 oxygens, and each has 6 electrons. So that's equal to 16 electrons. So we've got a lot to distribute this time. And again, carbon's going to be our central atom, and then we're going to have the 2 oxygens. So the first thing we're going to do is put a bonding pair between each. But carbon's not satisfied yet, so we'll put another bonding pair. So we'll make a double bond between each. That now satisfies carbon. We got 2, 4, 6, 8. But then oxygen only has 4, and there's also 8 more electrons to go around. So we're going to put 2 pairs on each, and then that should satisfy it. So 2, 4, 6, 8, 2, 4, 6, 8. Yes. So if we drew the display form, you would draw the double bonds and then the lone pairs of electrons like so. So there is a relationship between bond length and bond strength. So bond length is the distance between the nuclei of 2 atoms in a bond. And bond strength is the amount of energy required to break the bond. When bond length increases, so when the bond gets longer, the bond strength will decrease. So it'll be easier to break the bond as it gets longer. So one trend to be aware of is that group 17 elements form diatomic molecules. So if you remember, fluorine always exists as F2, bromine as Br2, chlorine Cl2, and so on. So as you move down the group, remember, their atomic radius will increase. So that means that the bond length increases, and then the bond strength will decrease. So if we look here, you can see that the radius, or the bond length, for fluorine is 143, it's 199 for chlorine, 228 picometers for bromine, and then 266 picometers for iodine. So these are successively longer, and because of that, the strength of those bonds gets weaker and weaker. Another example is that as you increase the number of bonds, the bond length will decrease and the bond strength will increase. So if you have a single bond between two carbons, the bond length is 153.51 picometers. You throw on an extra bond, so a double bond, you can see that the bond length decreased. And then if you have a triple bond, it decreases even more. So this would be the easiest bond to break. This one would be harder, and this one would be the hardest because it has the shortest bond length, so the strongest bond. Another way of looking at this is the bond order. So the number of bonds, that's the number of bonds between two atoms, and the higher the bond order, the stronger the bond. So a single bond has a bond order of 1, a double bond order of 2, triple bonds have a bond order of 3. So to find out the bond order for a polyatomic ion, you divide the sum of bond orders by the number of bonding groups. So if we look at carbonate here, we have a bond order of 2 here, a bond order of 1, and a bond order of 1. So we add them all together and divide by the number of bonds, and we find out that the bond order is 1.33. So now we'll talk about polar molecules, and we'll learn how to determine whether a molecule is polar or not. So now we're going to learn about polar covalent bonds. We learned about this a little bit earlier in an earlier lesson. We know that they occur when the delta N is between 0.5 and 1.7. So that's a polar covalent bond. And remember that a pure covalent bond is from 0 to 0.5. So anything higher than 0.5 would be a polar covalent bond. The shared electrons will be drawn closer to the more electronegative atom, and that creates something known as a dipole. So for example, oxygen has a higher electronegativity than hydrogen. So it will pull the shared electrons towards itself, and that'll give oxygen a partially negative charge. The charge is only partial only because oxygen doesn't fully pull the electron away. It's not like an ionic bond, but it is pulling the electron closer to itself, giving itself a negative dipole, and then hydrogen would have a positive dipole. So to determine whether a molecule is polar is a little trickier than figuring out if the bonds themselves are polar covalent. So a molecule might be entirely composed of polar covalent bonds, but they may actually be nonpolar. So to be classified as a polar molecule, the molecule has to have a slightly negative region and a slightly positive region. So it has to have dipoles. So this is obtained through one of two ways. One, an asymmetrical arrangement of bonds and atoms around the central atom, and lone pairs of electrons on the central atom. So both of these could apply, or one of them can apply to determine whether something is a polar molecule. So all of these examples are polar molecules. So there are two different ways to demonstrate that they're polar. So you can draw an arrow with a little cross notch here to point towards the more electronegative atom, or you can do like water and show the negative and positive dipoles. So the symbol, so this one would have the negative dipole, this one would have the positive dipole. I'm just going to make my pencil a little less thick. So nitrogen has the negative dipole. These all have a positive dipole, like so. And then the same thing here, positive dipoles, because they're the less electronegative, and then chlorine would have a negative dipole. So you can see that they're not symmetrical. You can't fold this in half and have the same thing overlap. This one here, ammonia, has a lone pair of electrons. So that's why this one would look the way it is. So The shape is determined by those lone pair of electrons. So no, and it's asymmetrical. You can't fold that up. This one, same thing. It's symmetrical around. Each of these are the same. And if this also had been the same, the hydrogen, if this was a hydrogen instead of a chlorine at the top, this would be nonpolar because all of these would be positive dipoles. But now we have a negative dipole and 3 positives. So this one's polar. Then water is extremely special. So this one has the dipoles already written, but you could also represent it this way. So the electrons are being drawn towards oxygen. So you may be required to draw dipoles on a molecule, and this is how you would do it. So just a recap of dipoles. So molecules with polar covalent bonds create dipoles. And like I said before, the atom with the higher electronegativity will pull the electrons it's sharing towards it, giving it a negative dipole, and the other one a positive dipole. So that's illustrated here too. This one is showing like the electron cloud is closer to bromine, but this is how you can draw it as well, that the 2 electrons are closer to itself than the hydrogen. So to be classified as nonpolar, a molecule has to be either symmetrical in bonds and atom arrangement or have nonpolar covalent bonds. So no end is slightly negative or slightly positive, or more negative or positive. So if you take a look here, so we have BF3. So these are polar covalent bonds, and the fluorines are more electronegative, so they're pulling the electrons towards each other. But if we drew our dipoles, these are all negative dipoles. So all along, they're equally pulling. So there's no end of this molecule that has a positive dipole and one end having a negative dipole. So this would be nonpolar. This one here, carbon tetrachloride, all these chlorines are pulling their electrons in their bonds towards themselves. And then the carbon is all by itself in the middle. It's symmetrical. You could fold on itself. It also has negative dipoles all the way around, so there is no one end that's more positive than the other. So this is also nonpolar. These ones down here, methane, it has nonpolar covalent bonds, so there are no dipoles at all. Same thing with oxygen. They're equally sharing the electrons because it's a nonpolar covalent bond. It's a double bond. So no end is slightly negative or slightly positive for these ones. So these are all nonpolar examples. So I found this resource from our Cognity textbook quite useful. So it's a summary of the 3 types of bonding. So we have ionic bonding. So that occurs between metallic and non-metallic elements. And there's a huge difference of electronegativity between the atoms. And these are held together through electrostatic attraction. Polar covalent bonding happens between atoms with a moderate difference in electronegativity. So remember, that's from 0.5 to 1.7 change. And you'll end up with dipoles, like shown here. And then finally, nonpolar covalent bonding, or pure covalent bonding, occurs between atoms with little to no difference in electronegativity. In our next lesson, we're going to spend quite a bit of time determining the shapes of molecules and learning some of the exceptions to the octet rule. But right now we'll just do a little touch on how we determine the shapes of molecules. So molecule shape depends on the arrangement of the atoms in the molecule and then lone pairs of electrons. So we'll talk about 3 today, but we'll talk about more on our next lesson. So tetrahedral means you have a central atom with 4 bonding pairs around it. So the example in this one is methane, so CH4. So this would be tetrahedral. Linear is when you have a central atom with 1 or 2 ligand atoms and no lone pairs of electrons. And then V-shaped or bent is when you have the central atom, you have 2 ligand atoms and then 2 lone pairs of electrons. So this is called bent or V-shaped. An example of this would be water. This one, carbon dioxide, and this one would be methane. But we'll spend some time building some molecules to determine that.